The night sky is a beautiful lie. Over 95% of the light in the universe is completely invisible to human eyes. This hidden illumination is not an emptiness, but a vibrant reality holding the keys to our cosmic origins and ultimate fate. By the end of this journey, you will see the universe in a completely new way, through the light it has been hiding all along. How did a faint microwave whisper become the most important fossil in existence? And what ghostly signal could finally reveal the identity of dark matter? The cosmos is broadcasting its deepest secrets on channels we are only now learning to tune into. Are you ready to see what has been hidden in plain sight? Our eyes are biological masterpieces, yet they operate with a severe cosmic restriction. They evolved to detect the specific wavelengths of light most useful for survival on Earth, primarily those emitted by our sun. This narrow sliver of reality, which we call visible light, spans from red to violet. Every color you have ever seen exists within this incredibly tight band. But step beyond its borders, and the universe transforms into something entirely different and mostly invisible. We are surrounded by a constant, silent symphony of radiation, from the long, gentle waves that carry radio broadcasts to the incredibly energetic bursts of gamma rays that signal the most violent explosions in the cosmos. Our eyes are deaf to this grand performance. It is as if we have been watching a magnificent play, but only from a single, fixed seat in the very last row, completely unaware of the elaborate sets, the intricate costumes, and the full cast of characters playing out just beyond our limited view. This fundamental blindness is the very reason we built new eyes, instruments that can finally perceive the universe in all its hidden glory. This vast cosmic keyboard stretches far beyond our narrow perception. Its full range is the electromagnetic spectrum, the complete catalog of every type of light. Think of it as a musical instrument of unimaginable size, with our visible colors representing just a handful of notes in the very center. On one side, the wavelengths grow longer and more gentle. Just beyond the red we can see is infrared radiation. You cannot see it, but you feel it every day as warmth on your skin from the sun. Further out, we find microwaves. These are the same waves that heat your food, but they also carry whispers from the infant universe. And at the far end of this long wavelength side are radio waves. These are the giants of the spectrum, so long that a single wave can be longer than a building. They carry music to your car stereo, but also the faint, ancient signals from exploding stars and colossal black holes. Now travel in the other direction from visible light, where the wavelengths become shorter, more energetic, and far more violent. Just past violet lies ultraviolet light, an invisible energy that can tan or burn your skin. Then come X-rays with their incredible power to pass straight through your flesh, allowing doctors to see your bones. At the very extreme end of the spectrum are gamma rays. These are the most potent form of light, each burst carrying more energy than 1,000,000 suns. They are born in the universe's most catastrophic events, from the collapse of massive stars to the collisions of dead stellar cores. Every one of these invisible bands is a different chapter in the cosmic story, a channel broadcasting a part of reality our eyes were never built to receive. To read this hidden story, we had to build new senses for ourselves, crafting incredible machines that can finally listen to the universe's silent symphony. These incredible tools are our bridges across the sensory void. To catch the long, lazy waves of radio light, we constructed colossal dishes that act like cosmic ears. These radio telescopes, some as wide as a mountain valley, Listen patiently for the faint whispers emitted by vast clouds of interstellar gas and the rapid-fire pulses from spinning stellar corpses called pulsars. Their immense size is necessary to gather enough of these gentle, stretched-out waves to form a clear signal. For the warmth of infrared light, which is easily absorbed and mimicked by our own atmosphere, we had to launch our eyes into the void. Space-based infrared telescopes, like the Spitzer Space Telescope, drift in the cold silence above Earth, peering into the dense, dusty cocoons where new stars are being born, seeing the heat of creation itself. To study the searing radiation of ultraviolet light from hot, young stars, we built specialized observatories that operate in the vacuum of space. They reveal stellar nurseries in dazzling detail, showing us stars in their violent, brilliant youth. Then there are the X-ray telescopes. Capturing this penetrating light requires a unique design, using sets of nested mirrors arranged at shallow angles, like stones skipping across a pond. This grazing incidence approach gently guides the high-energy X-rays to a focus, allowing us to see the final, furious glow of matter as it spirals at near light speed into the abyss of a black hole. At the most extreme end, gamma-ray detectors stand guard, waiting for the universe's most violent flashes. These instruments do not form pretty pictures in the conventional sense. Instead, they record the precise energy and direction of these unimaginable blasts, signals that can only be produced by events like the annihilation of antimatter or the cataclysmic collapse of a giant star's core. Each of these specialized instruments is more than just a camera. It is a translator, converting the silent, alien language of invisible light into data, graphs, and finally, into colors our brains can comprehend. They turn the unseeable into a story we can understand, and with these stories, we are now ready to investigate the oldest light in existence, a fossil glow that fills every cubic inch of the cosmos. This faint microwave static is the oldest story ever told. It is a cosmic fossil, the cooled and stretched remnant of the universe's fiery birth in the Big Bang. Known as the cosmic microwave background, or CMB, this signal is the most abundant light in the entire cosmos, a ghostly afterglow that fills every direction you could possibly look. To understand it, we need to rewind time to when the universe was not even 400,000 years old. Back then, the cosmos was not transparent. It was a searing, dense fog of particles and energy, a hot soup where protons and electrons were constantly scattering light, trapping it in a chaotic dance. But as the universe expanded, it cooled. In a pivotal moment, it cooled just enough for those protons and electrons to finally combine and form the first neutral atoms. In that instant, the fog lifted. The light that had been trapped for eons was suddenly set free, able to travel across the universe for the very first time. That first flash of liberation is the light we detect today as the cosmic microwave background, but it has not remained unchanged. The universe has been stretching for over 13 billion years, and as space itself expands, it stretches the light traveling through it. The once brilliant, high-energy light has been stretched and cooled so dramatically that its wavelength is now in the gentle microwave part of the spectrum. This is why it appears to us not as a blinding flash, but as a uniform, cold glow, just a few degrees above absolute zero. Yet this fossilized light is not perfectly smooth. It contains incredibly subtle variations, tiny patches that are ever so slightly warmer or colder than their surroundings. These minute temperature fluctuations are not random. They are the cosmic blueprints, the seeds of all future structure. The slightly denser, warmer patches held just a little more gravitational pull, eventually drawing in enough matter to form the first galaxies, the first clusters, and the vast cosmic web we see today. By reading this ancient map, we have found undeniable evidence for our cosmic origins and even uncovered hints of the universe's explosive growth spurt, a period of faster-than-light expansion called inflation that occurred in the first fraction of a second. This invisible light is the ultimate origin story, a baby picture of the cosmos that reveals how everything we know began. While the cosmic microwave background shows us the universe's first light, another form of invisible illumination reveals its ongoing creation. The cosmos is constantly forging new stars, but this dramatic process happens behind thick, dark curtains of cosmic dust. To our eyes, these stellar nurseries are impenetrable, appearing as mere voids or silhouettes against the brighter background of space. Yet within these dark clouds, the very dust that blocks our view becomes a beacon in the infrared. These microscopic grains absorb the intense visible light from newborn stars, heat up, and then re-radiate that energy at longer, invisible wavelengths. This is the magic of infrared astronomy. It transforms an opaque wall into a transparent window, allowing us to witness the violent and beautiful birth of stars and planetary systems. A perfect example lies in the iconic pillars of creation. In visible light, they are majestic, finger-like structures of cold gas and dust. But when viewed through the infrared eyes of the Hubble and James Webb Space Telescopes, the dust itself seems to vanish. The pillars become ghostly, ethereal frameworks, and their hidden interiors blaze to life, revealing brilliant, newly formed stars that were completely obscured before. This hidden infrared light shows us the earliest chapters of a star's life, from the initial collapse of a gas cloud to the fiery ignition of nuclear fusion. These processes are not just about creating new suns, they are cosmic forges where the intense heat and pressure inside young stars fuse simple elements into heavier ones like carbon, oxygen, and iron. The eventual death of these stars will scatter these essential ingredients across the galaxy, seeding future generations of stars, planets, and perhaps even life itself. By seeing this hidden light, we are not just watching star formation, we are tracing the origin of the very elements that make up our world and our bodies, connecting the birth of distant suns to the potential for life around them. While the infrared reveals cosmic forges, the radio universe speaks in a language of gentle whispers. At the longest wavelengths of light, the cosmos produces a quiet, persistent hum that tells a completely different story. This is not the violent light of creation or destruction, but the steady glow of everyday cosmic processes. One of the most fundamental sounds in this symphony comes from the cold hydrogen gas that drifts through the vast emptiness between stars. This simple atom, the most common element in the universe, naturally emits a faint radio signal at a very specific wavelength of 21 centimeters. It is a cosmic beacon for normal matter. By tuning our radio telescopes to this frequency, we can map the invisible skeleton of our own Milky Way galaxy, tracing the colossal spiral arms made not of stars but of this primordial gas. Another profound source is synchrotron radiation, a process where electrons caught in the grip of powerful magnetic fields spiral at nearly the speed of light. This motion forces them to give off energy, releasing a broad, faint radio glow that permeates entire galaxies. This light acts as a census of the high-energy particles that course through interstellar space, revealing the invisible magnetic architecture that binds a galaxy together. Then there are the most precise timekeepers in the cosmos, pulsars. These are the rapidly spinning, ultra-dense cores of exploded stars, known as neutron stars. As they rotate, they beam out intense radio waves from their magnetic poles like a cosmic lighthouse. If the beam sweeps across Earth, we detect it as an incredibly regular pulse, a clock so stable it rivals our best atomic timekeepers. The beauty of radio waves is their resilience. They can travel for billions of light years through clouds of dust and gas that would completely block visible light. This allows us to detect the most distant and energetic objects in the universe, like quasars, which are supermassive black holes at the centers of young galaxies, shining with the light of 1 trillion stars as they devour matter. This silent symphony provides a crucial inventory of the normal matter in the cosmos and reveals the dynamic, magnetic life of galaxies, setting the stage for the violent high-energy phenomena that await us. But the radio sky's gentle whispers give way to a far more intense and searing light. Ultraviolet radiation is the signature of the universe's most extreme environments, a blistering light that reveals stellar violence on a grand scale. This is the domain of the true cosmic titans, the O-type stars. These are not the gentle, long-lived stars like our Sun. They are monstrously large, incredibly hot, and live fast and die young, burning through their nuclear fuel in just a few million years. Their surfaces are so ferociously hot that they do not just glow with visible light, they flood their surroundings with intense ultraviolet radiation. To study this searing energy, we must rise above our own planet. Earth's atmosphere acts as a protective shield, absorbing the vast majority of this harmful ultraviolet light. While this is essential for life on the surface, it completely blinds our ground-based telescopes to the ultraviolet sky. Our only view comes from observatories in space, like the Hubble Space Telescope and the Galaxy Evolution Explorer, which operate in the vacuum above our atmosphere. Through their specialized eyes, the ultraviolet universe comes into sharp focus. By analyzing the precise fingerprints in this UV light, astronomers can take the temperature of these stellar infernos, determine their chemical composition, and even calculate their immense masses. But the story does not end with individual stars. This high-energy light also illuminates the largest and most elusive structures of a galaxy. Surrounding spiral galaxies like our own Milky Way are vast, invisible halos of incredibly hot gas. This gas is so thin and diffuse that it is completely transparent to visible light, rendering it invisible to traditional telescopes. Yet it is searingly hot, reaching temperatures of millions of degrees. Gas this hot naturally glows in ultraviolet and X-ray light. When we point our UV telescopes at a galaxy, we see this faint, enormous glow extending far beyond the familiar spiral disk of stars. These colossal reservoirs contain a staggering amount of normal matter, potentially solving a long-standing mystery of where a large fraction of a galaxy's expected mass has been hiding. This ultraviolet glow traces the entire life cycle of a galaxy's most energetic matter, from the violent birth of massive stars to the giant, simmering halo that governs its growth and evolution. It is a direct bridge to the even more violent and energetic phenomena that shape the cosmos, the cataclysmic events that unleash the most powerful light of all. X-rays illuminate a cosmos in the throes of extreme violence. This is the light of matter pushed to its absolute limits, heated to temperatures of millions of degrees. To produce such searing radiation, you need the most powerful forces in the universe, and nothing is more effective than gravity's ultimate grip. When vast clouds of superheated gas are trapped within clusters of galaxies, the largest structures held together by gravity, they glow intensely in X-rays, revealing a hidden web of matter that binds thousands of galaxies into a single, colossal entity. But the most concentrated sources of this high-energy light are found where gravity becomes an inescapable prison, around black holes and neutron stars. Here, gas does not simply fall in. It is ripped apart and whipped into a frenzied, glowing disk as it spirals toward the point of no return. Friction within this accelerating maelstrom heats the material to unimaginable temperatures, causing it to shine with X-rays just before it vanishes forever across the event horizon. We can never see the black hole itself, but this final, furious scream of light is its undeniable signature. Space-based observatories like Chandra and XMM Newton have tuned their vision to this brutal realm. They have mapped a sky crackling with explosive energy, from the intense flares of young stars to the expanding million-degree shockwaves left by supernova explosions, the scattered debris of dead stars. This X-ray vision shows us a universe in a constant, violent state of transformation, where matter is endlessly recycled under the most extreme conditions imaginable. It is a direct window into the behavior of space, time, and gravity pushed to their breaking point, a preview of the even more unimaginable power that creates the universe's final, most fleeting light. Gamma rays are the final, explosive scream of the cosmos. At the very peak of the electromagnetic spectrum, these photons carry unimaginable energy, each one a quantum bullet born from the most extreme violence the universe can produce. To find the events that create them, you must look to the deaths of the most massive stars in hypernova explosions, to the final, spiraling dance of neutron stars as they collide, and to the relativistic jets that supermassive black holes fire into the void at nearly the speed of light. These are not mere stellar flares, they are fundamental restructuring events that forge new elements and reshape entire regions of space. The most dramatic manifestation of this power is the gamma-ray burst. For a few fleeting seconds, a single gamma-ray burst can outshine every star in 100 billion galaxies combined, releasing more energy than our Sun will emit across its entire 10 billion-year lifespan. It is the single brightest electromagnetic event possible in the universe. We cannot see these flashes from the ground, as our protective atmosphere thankfully absorbs every last bit of their lethal radiation. To hunt them, we must send specialized detectors into the void, instruments like the Fermi Gamma Ray Space Telescope, which constantly scans the sky for these sudden, brilliant, and fleeting cosmic explosions. When these observatories record a gamma-ray burst, they are capturing the signature of matter being transformed under conditions we cannot possibly replicate on Earth. The intense blasts allow scientists to probe the absolute limits of particle acceleration, witnessing how matter behaves when pushed to energies far beyond the reach of our most powerful particle colliders. Furthermore, these cataclysms are cosmic forges for the heaviest elements. The violent mergers of neutron stars, in particular, are now understood to be the primary factories where atoms of gold, platinum, and other heavy elements are minted and then scattered across the galaxy. The gold in a wedding ring or the platinum in a catalytic converter was likely born in one of these spectacular, universe-shattering collisions billions of years ago. This ultimate frontier of light reveals a universe in a state of constant, violent creation, where the most destructive events are also the very sources of the complexity that makes our world, and even us, possible. Beyond the brilliant death cries of gamma-ray bursts lies a far more subtle and pervasive mystery. Woven throughout the entire gamma-ray sky is a faint, uniform glow whose source remains one of the greatest puzzles in all of science. This signal could be the ghostly signature of dark matter, the invisible substance that makes up over a quarter of everything in the universe. Dark matter is the cosmic architect we cannot see. Its overwhelming gravitational pull dictates how galaxies spin at speeds that should tear them apart, and it sculpts the vast cosmic web that defines the large-scale structure of the universe. Yet, for all its influence, it has remained utterly invisible. It does not emit, absorb, or reflect any form of light we know. It is a ghost that only makes its presence known by the gravitational pull it exerts on the things we can see. So, how could this ghost possibly produce a glow? The answer lies in some of the most promising theoretical ideas about what dark matter actually is. One leading candidate is a class of hypothetical particles known as weakly interacting massive particles, or WIMP. As the name suggests, these particles would be heavy and interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect directly. But according to some models, when two WIMP collide, they could annihilate each other in a flash of energy, transforming into a cascade of secondary particles that would ultimately include standard gamma-ray photons. This would not be a brilliant flash, but a faint, persistent whisper of gamma rays, a subtle background hum spread across the cosmos. To hunt for this ghostly signal, astronomers have turned their most sensitive gamma-ray telescopes, like the Fermi Space Telescope, toward places where dark matter is thought to be most densely concentrated. The centers of galaxies, including our own Milky Way, are prime hunting grounds, as are dwarf spheroidal galaxies. These small, faint satellite galaxies orbiting the Milky Way are believed to be made almost entirely of dark matter, making them perfect, clean laboratories to search for this annihilation signal without the interference of other bright gamma-ray sources. The search is painstaking, requiring scientists to meticulously subtract all the known sources of gamma rays from their data, the pulsars, the supernova remnants, the distant active galaxies, to see if a faint, unexplained excess remains. While a definitive, confirmed signal has proven elusive, several intriguing anomalies have surfaced over the years. Unexplained excesses of gamma rays from the galactic center and from certain dwarf galaxies have sparked excitement, though they could also be explained by more conventional, if unusual, astrophysical processes like undiscovered pulsars. The pursuit of this dark light is a testament to our ingenuity. We are searching for something that has never been seen, using the most violent form of light as our guide. A confirmed detection would be far more than just another discovery. It would be a monumental breakthrough, finally illuminating the identity of the universe's dominant form of matter and opening an entirely new window into the fundamental laws of physics. But beyond the violent crackle of gamma rays, the cosmos is flooded with an even more elusive form of energy. Trillions of ghost particles, called neutrinos, are streaming through your body at this very moment, completely unnoticed. These are not photons of light, but fundamental particles produced in staggering numbers by the universe's most powerful engines. The nuclear fusion that powers every star from our sun to the most distant giants creates a continuous torrent of them. A supernova explosion, the final death cry of a massive star, can release so many neutrinos that for a few seconds they outnumber all the atoms in the solar system. They are the silent byproduct of creation and destruction on a cosmic scale. Their ghostly nature comes from an almost unbelievable property. Neutrinos barely interact with anything. They can pass through a light year of solid lead as if it were empty space. This makes them fantastically difficult to catch, but it also makes them perfect cosmic messengers. Because they are unaffected by magnetic fields and unblocked by dust or entire galaxies, they travel in perfectly straight lines from their source, carrying pristine information across the universe. To have any hope of detecting these phantoms, scientists must build the most sensitive traps imaginable. These are not conventional telescopes. They are colossal arrays of sensors buried a mile deep in the Antarctic ice at the South Pole, in the clear waters of Lake Baikal, or in abandoned mines. These locations use the planet itself as a shield, blocking out all other cosmic interference so that only the rare, telltale flash of a neutrino collision can be seen. One of the most famous of these is the Ice Cube Neutrino Observatory, which transforms a cubic kilometer of pristine Antarctic ice into the world's largest and strangest scientific instrument. Within this dark, frozen volume, thousands of sensitive optical modules wait to record the tiny blue flash of light, known as Cherenkov radiation, that is produced on the exceedingly rare occasion a neutrino actually interacts with an atom. This diffuse, omnipresent background of neutrinos forms a kind of cosmic glow that is entirely separate from light. It is a whisper from the most shielded places in the universe. While photons from the sun's core can take 100,000 years to fight their way to the surface, neutrinos produced in the very same fusion reactions escape instantly, arriving at Earth just over 8 minutes later. They give us a real-time view into the heart of a star. When a star goes supernova, the light from the explosion can take hours to break through the outer layers, but the neutrinos arrive first, announcing the cataclysm before the visible fireworks even begin. By studying this ghostly background, we are opening a direct line of communication with the universe's most hidden forges, receiving unedited signals from places that electromagnetic light can never escape. This neutrino sky provides a crucial, independent confirmation of the picture we have built from light, and in some cases, it may one day reveal cosmic engines so hidden that they broadcast no light at all. In 2015, our perception of the cosmos shifted from sight to sound. Scientists recorded the faint, rhythmic chirp of gravitational waves, ripples in the very fabric of space-time that had been traveling for over 1 billion years. This was not a form of light at all, but a new kind of invisible energy, a vibration passing through the universe itself. Just as a stone dropped into a pond creates expanding rings, the collision of two immensely dense objects, like black holes, sends out gravitational ripples that stretch and compress everything in their path, including the space we occupy. These waves are so faint that by the time they reach us, the distortion they cause is smaller than the width of a single proton. To hear such a quiet cosmic whisper, we had to build the most sensitive measuring devices ever conceived. Observatories like LIGO in the United States and Virgo in Europe are colossal L-shaped instruments with arms several kilometers long. Inside these vacuum-sealed tubes, lasers race down tunnels, bouncing between mirrors suspended with incredible precision. When a gravitational wave passes through Earth, it minutely changes the length of one arm relative to the other, and this tiny shift, just a fraction of the width of a proton, creates an interference pattern in the laser light that scientists can decode into a sound. This is how we listen to the universe singing. The true power of this new sense emerges when it works in concert with our telescopes. In 2017, LIGO and Virgo detected the gravitational waves from two neutron stars spiraling together. Within seconds, observatories around the world and in space were alerted, and they swiveled to look at that same patch of sky. They saw a brilliant flash of light across the spectrum, from gamma rays to visible light to radio waves. This event, known as Multi-Messenger Astronomy, was like watching a silent movie of a cosmic collision while simultaneously hearing its soundtrack. The gravitational waves told us about the masses and the dynamics of the merger itself, while the light revealed the aftermath, including the creation of heavy elements like gold and platinum. By combining what we hear with what we see, we are no longer just observers of the cosmos. We are witnesses to its most dramatic events, feeling the very vibrations of reality as they unfold. This hidden light also illuminates our own celestial neighborhood. The planets and moons within our solar system broadcast a rich tapestry of invisible signals, each one revealing a world far more complex than our eyes alone could ever perceive. Venus, shrouded beneath a perpetual, crushing blanket of sulfuric acid clouds, is a perfect example. To our eyes, it is a featureless, brilliant white dot. But when we aim radar and radio telescopes toward it, those opaque clouds become as transparent as glass. These long wavelengths punch straight through the haze, bouncing off the volcanic plains and towering mountains below to send back a detailed map of the surface. We have discovered vast lava flows, colossal volcanoes, and bizarre, deformed terrain called tesserae, painting a picture of a geologically active and hellish world, all seen with light we cannot see. The giant planets Jupiter and Saturn are powerhouses of radio emission. Their immense magnetic fields, the strongest in the solar system, act like colossal engines. These fields capture charged particles, whipping them around at tremendous speeds. This violent interaction, especially with volcanic moons like Jupiter's Io, generates intense decametric radio waves that crackle and pop, creating a natural radio storm that we can listen to from Earth. This invisible radio light is a direct probe into the heart of their magnetic dynamos and their complex gravitational dances with their families of moons. Even the cold, distant dwarf planet Pluto tells its story in infrared. From such a vast distance, the visible light we receive is faint, offering little more than a blurry, reddish disk. But every object with a temperature above absolute zero glows with infrared light, a thermal signature of its warmth. By analyzing Pluto's faint infrared glow, the New Horizons spacecraft could precisely measure its surface temperature, a frigid -380 degrees Fahrenheit, and identify the specific ices on its surface, from nitrogen and methane to carbon monoxide. This application of invisible light transforms every asteroid, moon, and planet from a silent, distant point of light into a dynamic, physical world with a story to tell. We are using these hidden channels to assess atmospheres, hunt for subsurface oceans on icy moons, and understand the fundamental processes that shape planetary evolution, bringing the search for habitability from the theoretical realm right into our own cosmic backyard. Our planet's atmosphere is a life-saving shield, but it is also a cosmic sensor. This thin, fragile blanket of gas that allows us to breathe performs a constant, invisible act of protection, filtering out the universe's most dangerous radiation. It brilliantly blocks the vast majority of ultraviolet light, and it stops every single X-ray and gamma ray from reaching the ground. Without this natural barrier, the surface of Earth would be bombarded by energy capable of shredding our DNA, making life as we know it impossible. Yet this vital protection comes with a profound cost. It renders most of the universe's light completely invisible to anyone standing on the surface. For centuries, this meant our view of the cosmos was limited to the one narrow band of light the atmosphere lets through almost unscathed, visible light, and even that view is blurred and distorted by the swirling currents of air we call seeing. This is why traditional observatories with their great optical domes were built on high mountains to rise above as much of this turbulent layer as possible. The atmosphere's censorship, however, is not absolute. It possesses a few surprising windows. Just as it lets visible light pass, it is also largely transparent to the long, gentle waves of radio light. This fortunate transparency is the sole reason why radio astronomy could be born and flourish from the ground, allowing us to build those colossal dishes that listen to the whispers of cold hydrogen gas and distant pulsars. The case of infrared light is more complex. Our air is mostly opaque to it because the water vapor and carbon dioxide molecules in our atmosphere are excellent at absorbing infrared radiation. Yet there are a few specific, narrow bands of infrared wavelength that can slip through this molecular net. These are the atmospheric windows, and astronomers seek out the driest, highest places on Earth, like the peaks of Mauna Kea in Hawaii or the Atacama Desert in Chile, to place their infrared telescopes and peer through these precious, clear panes into the universe. This fundamental limitation, this reality that our safe haven is also a sensory prison, has been the single greatest driver of astronomical progress in the last century. It forced our ingenuity to new heights, literally. We had to launch our eyes above the veil. The development of rockets and satellites was not just about reaching space, it was about seeing the universe for the first time. Every space telescope, from Hubble to Chandra to James Webb, is a direct result of our need to escape our atmospheric blindfold. Our planet's greatest gift to life is the very thing that forced us to become a spacefaring species to truly understand the cosmos. Our ability to perceive this hidden cosmos is a testament to pure human ingenuity. Each new window into the electromagnetic spectrum demanded its own revolutionary technology, a custom-built key for a previously locked door. To catch the faint warmth of infrared light, for instance, the detectors themselves must be colder than the space they are observing. This requires sophisticated cryogenic systems, cooling the sensors to within a few degrees of absolute zero to prevent their own heat from blinding them to the delicate cosmic signals. Without this deep freeze, the infrared universe would remain forever invisible. The challenge is even more extreme for X-ray vision. You cannot simply reflect high-energy X-rays like visible light off a standard mirror. They would burrow straight through the surface. The solution was an engineering marvel called grazing incidence. X-ray telescopes use sets of nested, barrel-shaped mirrors, meticulously polished and aligned so that the incoming photons strike them at a shallow angle, like a stone skimming across a pond. This gentle glancing blow allows the mirrors to guide the X-rays to a focus, capturing the violent glow of matter heating to millions of degrees. This technological arms race extends to every part of the spectrum. Radio astronomers weave together networks of dishes spanning continents to create a virtual telescope the size of the Earth itself, achieving resolution so sharp they could spot a coin on the lunar surface. Gamma-ray hunters develop crystals that flash with light when struck by these cosmic bullets, translating unimaginable energies into something we can measure. Every one of these instruments is a masterpiece of material science and precision engineering, built to answer a simple, profound question: what is out there that we have not yet seen? The result of this relentless pursuit is more than just data. It is a new way of seeing. We assign colors to these invisible wavelengths, creating stunning images where the vibrant hues are not what our eyes would perceive, but a translated map of temperature, energy, and composition. A brilliant purple might represent the X-ray blaze from a black hole's disk, while a deep red glow could trace the cold dust of a stellar nursery in infrared. These are not false pictures, they are true portraits of the universe, painted with a palette of light our biology never provided. This ongoing revolution proves that our cosmic exploration is not truly limited by the light that exists, but only by the brilliance and creativity we muster to perceive it. This layered vision transforms a simple snapshot into a living biography of a galaxy. Take our own Milky Way, a familiar river of stars in our night sky. That beautiful band of light is only the opening chapter. When we overlay the view from a radio telescope, the galaxy's invisible skeleton materializes, tracing vast, swirling arms of cold hydrogen gas where future stars will be born. Switch to the infrared, and the dark lanes that seem to split the Milky Way suddenly blaze with the warmth of thick dust clouds, the very cradles of stellar creation. Aim an ultraviolet telescope at the same region, and brilliant, hot blue stars ignite across the spiral arms, pinpointing stellar nurseries only a few million years old, cosmic infants in their fiery youth. Finally, direct an X-ray observatory toward the galactic center, and the serene star field gives way to a violent, energetic heart. You see the searing glow of million-degree gas, the fading embers of supernova explosions, and the intense pinpoint of our own supermassive black hole, Sagittarius, a star, as it occasionally flares with activity. Each of these perspectives is true, yet each tells a completely different story about the same object. A quasar that appears as a single, brilliant star in visible light might reveal itself in radio waves to be ejecting colossal jets of matter millions of light years long. A seemingly calm, elliptical galaxy can be hiding a ferocious X-ray core, betraying a hidden feeding frenzy at its center. This is the fundamental revelation of multi-wavelength astronomy. Objects are not one thing, they are many things simultaneously, and to see only one version is to misunderstand them completely. This holistic approach uncovers the deep, interconnected cycles that govern cosmic evolution. We can now trace how the intense ultraviolet radiation from massive stars blows gigantic bubbles in the surrounding gas, how supernova shockwaves from those same stars' deaths trigger the next wave of star formation, and how the supermassive black hole at the galaxy's core, revealed in X-rays, can either pour energy back out to stifle star birth or allow it to proceed. It is a continuous feedback loop, a cosmic dialogue between the very large and the very small, and we are only able to hear the entire conversation because we learn to listen on every channel. The universe is a multi-sensory experience, and we are finally building the instruments to appreciate its full symphony. When we tally up all the light in the cosmos, the numbers tell a humbling story. All the stars in every galaxy, every brilliant spiral and swirling nebula we can see, contribute less than 1% of the universe's total electromagnetic energy. They are the glittering decoration on a far more substantial structure. The true heavyweight of the cosmic energy budget is the ancient whisper of the cosmic microwave background. This fossilized glow from the Big Bang itself makes up the overwhelming majority of all light, a relic so pervasive it outshines everything else combined. After this primordial echo, the background hum of the universe takes over, a diffuse fog of infrared light emitted by warm dust throughout cosmic history adds a significant portion. Then comes the combined X-ray glow from countless distant black holes and hot gas clouds, along with the accumulated gamma-ray flicker from the most violent explosions. These unresolved backgrounds, where the light from billions of individual sources blends into a cosmic chorus, represent a major share of the budget. This accounting reveals a profound truth. The universe we perceive with our eyes, that breathtaking tapestry of stars, is merely the visible tip of a colossal, invisible iceberg. The cosmos is not primarily a place of starlight. It is a realm dominated by the cooled remnant of its own creation, and by the steady, diffuse glow of processes that are either too faint, too ancient, or too energetic for our biological senses. This cosmic energy budget rewrites our place in the grand scheme, showing us that what we see is a beautiful but minor detail in a story written overwhelmingly in invisible light. Amidst the universe's chaotic radio whisper, a profound question lingers. Could one of those signals be a deliberate hello? The search for extraterrestrial intelligence, or SETI, is a monumental effort to find an artificial pattern in the cosmic noise, a needle of purpose in a haystack of natural phenomena. Scientists are not listening for complex messages or alien music. They are hunting for something far more fundamental, a signal that nature cannot easily produce. This would be a narrow-band transmission, a radio wave focused on one specific frequency with laser-like precision. In the wild, natural radio sources like pulsars or the glow of interstellar gas create a broad, messy smear of frequencies. A deliberate signal, however, would stand out as a sharp, pure tone, a technological fingerprint revealing an engineered origin. This search is a testament to patience and scale. The Allen Telescope Array, a dedicated SETI facility, can observe multiple star systems simultaneously, listening across a wide range of frequencies. Other projects use the downtime of massive radio dishes, scanning the sky while they perform other astronomical duties. Yet the challenge is almost beyond comprehension. The universe is drowning in radio static, from the faint hiss of ancient hydrogen to the roaring blast of distant quasars. Finding an artificial signal is the ultimate cosmic eavesdropping mission, straining to hear a single, structured whisper in a hurricane of random sound. The logic behind this radio search is deeply compelling. Of all the forms of invisible light, radio waves are uniquely suited for interstellar communication. They can travel for thousands of light years through the vacuum of space with very little energy loss, piercing through cosmic dust clouds that would block visible light. They are the universe's most reliable long-distance couriers. If another civilization wanted to announce its presence across the vast galactic distances, a radio beacon would be a logical and efficient choice. For decades, this search has continued, punctuated by moments of thrilling but fleeting excitement. The famous WOW signal, detected in 1977, was a powerful, narrow-band burst that matched the profile of an artificial signal perfectly. It lasted for 72 seconds and was never heard again, a cosmic siren song that remains one of the greatest unsolved mysteries in the field. While no signal has ever been confirmed, the silence is not a verdict. It simply means we have not yet heard the right signal on the right channel at the right time. The search itself reframes our place in the cosmos, transforming the universe's litter of invisible light from a backdrop of natural processes into a potential communication network. Every silent frequency scan is not a failure, but a step toward a possible future where the static parts, and we realize we have been living in a crowded galaxy all along, simply waiting to tune into the right conversation. This realization shatters any naive notion that our eyes show us the true face of the cosmos. If over 95% of the universe's light is invisible to us, then how much of reality are we actually perceiving? The answer is a staggeringly small slice. Our senses were not designed to understand the cosmos. They were honed by evolution for survival on Earth. They tell us when fruit is ripe, help us spot predators in the grass, and allow us to navigate a world dominated by the particular light our sun emits. They are practical tools for a specific environment, not universal truth detectors. The entire electromagnetic spectrum, from the long, lazy radio waves to the searing blast of gamma rays, is just as real as the red of a rose or the blue of the sky. The only difference is that we are biologically blind to it. This forces a profound philosophical shift. For centuries, humanity placed itself at the center of creation, believing our perspective was the definitive one. We now know this is a cosmic illusion. We are not the audience for whom the universe performs, and our senses are not the ultimate arbiters of what is real. We are merely inhabitants of a small world, equipped with a limited set of biological instruments, trying to decipher a symphony that is mostly playing in notes we cannot hear. The true nature of reality is far richer, more complex, and more astonishing than our direct experience could ever suggest. It is a reality hidden in plain sight, one we can only access by transcending our biology. We have done this not with new senses, but with the power of human reason, the universal language of mathematics, and the brilliant extension of our perception through technology. Our telescopes and detectors are not just machines, they are philosophical instruments, proving that what is real extends infinitely beyond what we can feel. This emerging era of multi-messenger astronomy is transforming our role from spectators to participants in the cosmic drama. We are no longer merely looking at the universe, we are feeling its vibrations and catching its ghostly particles, creating a multi-sensory experience of reality itself. The power of this approach is its profound synergy. A single cosmic cataclysm, such as the collision of two neutron stars, is no longer a single data point. It becomes a rich, multi-chapter story. First, we feel it, the faint chirp of gravitational waves washing through Earth, telling us the masses of the objects and the nature of their final spiral. Seconds later, space-based gamma-ray detectors record the brilliant flash of the initial impact. Then, telescopes around the world and in orbit swing into action, capturing the event's afterglow as it blooms across the electromagnetic spectrum. They see the visible light of the expanding fireball, the infrared glow of newly forged heavy elements, and the persistent radio hum of the lingering debris. And if we are incredibly fortunate, our deep ice neutrino detectors might even register a handful of the elusive particles blasted out from the heart of the maelstrom. Each messenger provides an independent, corroborating piece of the puzzle. The gravitational waves confirm the dynamics of the merger, the light reveals the chemical composition and energy of the outflow, and the neutrinos offer a direct glimpse into the hyper-dense core of the event. This is not just adding more data, it is about achieving a verified, three-dimensional understanding that any single observation could never provide. The future of this field is accelerating at a breathtaking pace. The James Webb Space Telescope, with its unparalleled infrared vision, is poised to dissect the chemical fingerprints of such cosmic explosions in unprecedented detail, identifying the specific heavy elements created in these stellar forges. On the horizon, the LISA mission, a space-based gravitational wave observatory, will open a new low-frequency window, allowing us to hear the mergers of supermassive black holes, events so colossal they shake the fabric of spacetime for years. We are building a cosmic internet of observatories, all linked and listening, waiting for the next event to trigger a global symphony of discovery. This is the final step in our journey beyond visible light, moving from seeing a silent movie to experiencing the universe in full, immersive detail, with all its invisible channels playing in harmony. The same invisible light that illuminates cosmic history also holds a veto over its future. Across the vast gulfs between galaxies, a silent battle rages, one we can only see through the high-energy part of the spectrum. In the hearts of brilliant quasars and within frenzied starburst galaxies, torrents of ultraviolet light and X-rays flood into intergalactic space. This relentless energy barrage heats the sparse gas that drifts between galaxies, keeping it so hot and agitated that it cannot cool down, collapse, and coalesce into new stars. This process, known as feedback, acts as a cosmic thermostat, actively suppressing star formation and putting a hard limit on how large a galaxy can grow. The most luminous objects in the universe are using their invisible light to snuff out the very seeds of future starlight, governing the life cycle of galaxies from billions of light years away. But an even more profound transformation is underway, driven by the mysterious force of dark energy. The expansion of the universe is not just continuing, it is accelerating. As space itself stretches, it pulls on the very fabric of light traveling through it. Over billions of years, this relentless stretching will systematically drain the energy from every photon in the cosmos. The brilliant blue light of young, hot stars will be stretched to red, then to infrared, and then fade entirely from view. The fossil glow of the cosmic microwave background, the universe's first light, will cool and stretch further into the microwave band, becoming so faint and spread out that it will eventually be indistinguishable from the cold, empty void. In a future so distant it defies comprehension, the night sky will be profoundly and permanently dark. The last generations of stars will have burned out, and the galaxies they called home will have been pushed beyond the visible horizon by the accelerating expansion. The cosmos will be a sea of undetectable radio waves, the final, stretched-out echo of a vibrant past that has faded into silence. By learning to read the invisible light of today, we are not just uncovering the story of how everything began, we are reading the final chapter, written in the slow, inevitable cooling of the universe itself. This hidden cosmos is a realm of physical law, not mystical energy. The same invisible light that reveals black holes and galactic halos is sometimes misunderstood or misrepresented in popular culture. You might hear claims about human auras as colored light fields, or warnings about dangerous cosmic energies constantly bombarding us. It is crucial to separate the genuine wonder of astrophysics from pseudoscience that borrows the language of science without its evidence. Authentic harmful radiation does exist in the form of ionizing waves like ultraviolet, X-rays, and gamma rays. Their high energy can indeed damage cells and DNA, which is precisely why our atmosphere blocks most of them and why we wear lead vests during medical X-rays. But the natural cosmic background of this radiation is incredibly faint. The random gamma ray from a distant galaxy or the ubiquitous microwave background glow is millions of times weaker than any medically significant dose. The radio waves that have traveled for billions of years to reach our telescopes are vastly weaker than the signal from your own cell phone held to your ear. You are in no danger from the silent symphony of the cosmos. As for the concept of a visible human aura, no scientific instrument, no matter how sensitive, has ever detected an energy field around a person that corresponds to these descriptions. What is often perceived as an aura is much more likely a fascinating interplay of psychology and perception, perhaps a form of synesthesia where one sense involuntarily triggers another. Understanding the true nature of this invisible light is its own form of power. It replaces vague fears and mystical claims with a concrete and far more breathtaking reality. We are not surrounded by mysterious, harmful forces, but by the faint, cool fossil of creation, the gentle whisper of atomic hydrogen, and the distant, searing signatures of black holes. This real story requires no embellishment. It empowers us to appreciate the universe for what it truly is, a physical system we can understand through reason, measurement, and our own brilliant ingenuity. You do not need a doctorate or a private observatory to become an explorer of the invisible sky. The vast torrents of data flowing from our most advanced telescopes present a unique challenge. There is simply too much information for any small team of scientists to analyze alone. This is where citizen science transforms every curious person into a vital research partner. Online platforms host projects where anyone with a computer and an internet connection can help professional astronomers make genuine discoveries. In the Radio Galaxy Zoo project, for instance, volunteers examine images that combine radio and infrared light. Their mission is to match the colossal, often contorted radio jets, which can stretch for millions of light years, with the specific galaxy that launched them. This is a pattern recognition task where the human brain's incredible ability to recognize shapes and connections still far surpasses even the most sophisticated algorithms. Your eyes can spot what a machine might miss. Other projects invite you to classify the flickering light curves of distant gamma-ray bursts, hunting for subtle clues about the nature of these cosmic explosions, or to sift through the data from gravitational wave observatories, listening for the faintest new ripple in spacetime. Each click, each classification is a piece of a global puzzle. When thousands of people contribute, their collective effort cleans and labels massive datasets, enabling professional researchers to focus on the biggest questions. This is the ultimate democratization of discovery. You are not just learning about the cosmos, you are actively helping to map its hidden structures, turning the overwhelming flood of invisible light into a collaborative, human endeavor to comprehend our universe. These breathtaking cosmic portraits are a translation of data into a language our eyes can understand. Since our biology fails us, astronomers use a powerful technique called false color to map the invisible onto the visible spectrum. They assign specific colors like red, green, and blue to represent different invisible wavelengths or levels of energy. An image dominated by infrared light, which we perceive as heat, might be rendered in deep reds and fiery oranges to evoke a sense of warmth. A view from an X-ray telescope capturing the most violent and energetic processes is often translated into cool blues and brilliant purples, colors we instinctively associate with intense power. It is crucial to understand that these images are not fabrications or artistic guesses. They are meticulous and accurate data visualizations. Every pixel corresponds to a real measurement of photons, and the chosen color scheme is a consistent code that reveals structure, chemical composition, and temperature differences our eyes would never detect. The iconic Chandra X-ray observatory images of supernova remnants, like the Crab Nebula, are perfect examples. In these pictures, ethereal blue and purple rings and clouds trace the searingly hot, expanding shockwave from a stellar explosion, while the brilliant white pinpoint at the center marks the spinning neutron star powerhouse left behind. Conversely, the James Webb Space Telescope's infrared vision paints the cosmos in hues of gold and crimson. Its view of the Carina Nebula, for instance, shows towering cosmic cliffs of dust glowing with a warm, amber light, revealing the stellar nurseries hidden within. These are not just pretty pictures, they are fundamental tools of discovery. The beauty we see is a direct byproduct of the physical reality being measured, unveiling a universe of sublime and hidden artistry that has been there all along, waiting for us to find the right palette to bring it into view. This relentless pursuit of invisible light has given humanity more than just cosmic knowledge. It has reshaped the very fabric of our daily technology. The challenge of capturing a single photon from a distant galaxy has repeatedly forced us to invent new tools, and those tools have a remarkable habit of finding their way into our pockets and our hospitals. Consider the digital camera. The heart of every smartphone camera is a sensor called a charge-coupled device, or CCD. This technology was not born in a consumer electronics lab. It was perfected by astronomers desperate to capture the faintest glimmers of starlight with far greater efficiency than photographic film. The same tiny silicon chip that now takes a family photo once counted individual photons from a quasar billions of light years away. This transfer of innovation extends to the medical field. The complex algorithms developed to sharpen the blurry, grainy images from early X-ray telescopes to tease out subtle details from a cosmic explosion became the foundation for the image processing software used in modern CT scanners and MRI machines. When a doctor examines a cross-section of your brain to locate a tiny anomaly, they are using a form of vision honed by the needs of X-ray astronomy. Even our handling of information has been transformed. The sheer, staggering volume of data pouring from every telescope, a deluge of ones and zeros describing the entire electromagnetic spectrum, overwhelmed traditional analysis. This pressure to make sense of the cosmic firehose directly accelerated the development of the very tools we now call big data analytics and machine learning. The patterns these algorithms find in the light of a million galaxies are the same patterns that now help predict weather, recommend movies, and diagnose disease. Perhaps most fundamentally, the entire science of radio astronomy, born from our desire to hear the whispers of hydrogen gas and pulsars, provided the foundational principles for modern wireless communication. The quest to understand the universe's silent symphony did not just satisfy our curiosity, it built the technological world we live in, proving that the most abstract questions can yield the most concrete and life-changing answers. This challenge of translation is met every day in planetariums and science centers around the world. These spaces have become theaters for the invisible, using immersive technology to wrap visitors in the hidden light of the cosmos. Under a domed ceiling, you can watch as the familiar star field of the night sky is suddenly overlaid with the swirling, ethereal structures of infrared dust clouds or the violent, purple glow of X-ray gas erupting from the galactic center. These are not just films, they are sensory journeys that allow you to step inside the multi-wavelength portraits we have been building. The goal is to create a moment of genuine awe, to make you feel the scale and the mystery of a reality that exists just beyond your biological grasp. To build a foundational understanding, educators turn to powerful, everyday analogies. They might explain the electromagnetic spectrum as a grand piano, where our eyes can only hear the middle octave, while the left-hand keys play the low, rumbling notes of radio waves and the right-hand keys play the high, tinkling pitches of gamma rays. Or they compare it to a rainbow stretched far beyond its ends, into colors like infrared and ultraviolet that we can only describe but never truly see. These simple comparisons demystify a complex idea, creating a mental model that anyone can carry with them. The most effective learning, however, happens when you can touch the invisible yourself. In classrooms and museum workshops, students use simple materials to build their own spectrometers from cardboard and old DVDs, discovering they can split the light from a light bulb into its constituent colors, just as astronomers do with distant stars. They borrow infrared cameras and point them at everyday objects, watching in real time as the cold glass of a window appears dark while their own warm hand glows brightly, visualizing heat as a form of light. These hands-on activities transform an abstract concept into a personal discovery, proving that the universe's hidden channels are not just for powerful telescopes, but are governed by physical laws that we can all explore. This educational mission is about more than just sharing cool facts. It is an investment in our collective future. By sparking a sense of wonder about the invisible cosmos in a young student, we are potentially inspiring the astronomer who will one day decode the dark matter signal, the engineer who will build the next generation of space telescopes, or simply a citizen who values evidence and reason in a complex world. Making the invisible visible in the classroom is a fundamental act of cultural stewardship, nurturing a society that understands its method for uncovering truth and feels a deep, humbling connection to the vast and mysterious universe we are so fortunate to call home. Our current map of the cosmos, for all its detail, is still missing entire continents. We have built instruments to see from radio waves to gamma rays, yet we are almost certainly surrounded by forms of energy and radiation that remain completely unknown, cosmic whispers on channels we have not yet learned to tune into. The greatest of these mysteries is dark energy, the force driving the universe's expansion to accelerate. This is not just an empty label, it is a fundamental gap in our understanding. What kind of engine could power such a thing? Does it produce its own faint, undetectable radiation, a new kind of light that simply passes through our detectors and our very bodies without a trace? The possibilities stretch even further. The standard model of physics, our most complete catalog of particles and forces, is known to be incomplete. Could there be entirely new particles or exotic fields that interact with light in ways we have not yet imagined? Perhaps they subtly twist the polarization of starlight as it travels for billions of years, or create a faint, universal background hum that our current technology is too crude to hear. The entire history of astronomy is a lesson in this kind of revelation. Every single time humanity built a new eye, a new telescope for a previously invisible part of the spectrum, it did not just add details to the existing picture. It unveiled entirely new classes of objects and phenomena. Radio telescopes revealed pulsars and quasars. X-ray vision uncovered the searing violence around black holes. Before these tools existed, we did not even know to look for these things. They were hiding in plain sight, in the silence. This pattern guarantees that our current view is still provisional. It is a humbling and profoundly exciting thought that the universe is likely filled with more invisible light, more hidden messengers, waiting for the next generation with even more ingenious tools to finally bring them into view. The static of the cosmos is not just noise, it is a promise, and we have only just begun to listen. Our journey through the invisible cosmos reveals a universe of profound and hidden grandeur. The silent symphony of radiation, from the ancient microwave whisper to the violent scream of gamma rays, is not an emptiness but a breathtaking plenitude. Every unseen wavelength is a different verse in the epic poem of existence, telling the story from the first flash of liberation to the final, fading embers of stars. This reality fundamentally challenges our place in the cosmos. We are not central observers in a universe designed for our senses. We are inhabitants of a small world, equipped with biological tools that show us only a sliver of what is truly there. The astronomer Carl Sagan perfectly captured the spirit of this quest when he said, "Somewhere, something incredible is waiting to be known." For us, that something is written overwhelmingly in the language of invisible light. It is a constant, humbling reminder that the universe is saturated with wonders, most of which remain just out of sight, waiting for our persistent curiosity and brilliant ingenuity to finally bring them into view. What form of invisible light bends your mind the most, the ancient fossil glow or the ghostly signal of dark matter? Let us know in the comments and join us as we continue our journey to the very edge of understanding.